Hello everyone, we are continuing on with our with projectile motion. This is 1.52, and this is these projectile motion problems are where something is launched at an angle above the horizontal, but it is caught at the same height, or it lands at the same height. So in this case, it's going to have both velocities in the x and y direction. Okay, so again, please start your homework and do the reading. Okay, do your OpenStax reading if you're using the OpenStax textbook, but if you're using Coletta, use a Coletta textbook too. Okay, and I've got those chapters listed there. Okay, let's continue moving on. So again, we're using the same problem-solving strategy that we used with the horizontal launch stuff. We're using the same problem-solving strategy now. With the horizontal launch problem, by the way, just to remind you that I'm going to mark up this document. With the horizontal launch problem, we didn't consider a velocity in the y direction. Okay, and things were falling below its initial position. Okay, so but with now, the difference is now. So the difference is, so it has no initial velocity in the y direction and is falling below its initial height. Well, now it is going to have an initial velocity, and it's going to be launched and caught at the same height. So if I throw a ball to my twin, he's going to catch it at the same height that I launch it, right? So that's kind of weird. Its initial position and its final position is going to be 0 meters, right? 0 meters off the ground. Or, well, I'm like 6'2", so whatever. Anyways, my point is it will have an initial velocity in the y direction, and that means, and also an initial velocity in the x direction, which means it's going to have a velocity like at an angle. So they're going to give you an initial velocity at an angle, and then you're going to have to find the initial velocity in the y direction and the initial velocity in the x direction, right? So let's just do that real quick. Let's remind each other, right, what that is. So sine of theta, actually, let me use red. So sine of theta, I think blue was better. Actually, black might be best. Okay, yeah. So sine of theta is equal to opposite over hypotenuse, which in this case would be, if this is theta here, that would be VIY over VI. So that means to get VIY is going to be equal to VI, the hypotenuse sine of theta. So that means VIY is going to be VI sine of theta. Okay. In the x direction, well, cosine of theta is going to be equal to adjacent over hypotenuse, and adjacent is VIX over VI. So that gives us VI cosine of theta is equal to VIX, and so VIX is VI, is the initial launch velocity, cosine of theta. Okay, so that trigonometry that I've been prepping you for is going to come into play, and also that vector addition is going to be important too. Something is launched up and to the right, you deconstruct that into its component vectors, which is going to be the initial x direction vector added to the initial y direction vector, which will make the total initial velocity vector. Okay? So we're going to be using basically this as our construct. Okay? And this is the type of situation that I'm talking about. So there's some cool things that kind of happen when you launch something from initial velocity. Okay? you'll see it. So if you shoot a ball up and to the right, this is y versus x. So this is up versus right. It's being launched at initial velocity up and to the right. Well, then it's going to reach some height right here. Well, now it's at its maximum height right at that point, right? Well, at that point, its velocity is only going to be in the x direction. Okay, all of its velocity, and I don't know why I put a sub y there, it's not going to be equal to the initial velocity. It would be a velocity vector shorter than that. It's going to slow down. It's going to be slowing down as it's moving upwards. And then it's going to start speeding up, back up, as it's moving downwards. And the cool thing about this is the initial velocity upwards is going to be equal to the initial velocity downwards, down to the right. So if you throw a ball really hard up into the air, it's going to be coming back down at the same speed that it was launched into the air. And the other really cool point, too, is where it reaches its max height is also where it reaches its half time of flight. So if it takes it, it reaches the total time of flight is delta t, so it'll reach its peak height at half that time of flight. Okay, so there's a lot of cool things that we could talk about when we do this. So this is another description of that type of a problem. Okay, so when we're looking at the vectors, okay, it's being launched at this vector, and notice that its velocity vector initially is a huge vector up and to the right, and that's equal to its vector down and to the right as it's coming down. So this vector here is equal to this vector right here. Okay, and notice that the length of this vector is getting smaller and smaller and smaller, and that's because the y direction portion is getting smaller. Notice the x direction portion is the same size. Okay, and it's in fact equal to this size. So since its velocity, so at the moment where it reaches its maximum height right here, the velocity at that point is the constant velocity vector. Okay? Well, that's illustrated really well in this diagram right here. Okay? So here we have that same example. And so Jake is going to throw a ball at a 60-degree angle up and to the right, and then Jim is going to catch it over here, right? So this angle right here is 60 degrees. All right. Now, if you notice, this is its initial velocity vector, and this is its final velocity vector. Okay. So when it gets to this height right here, notice that as it's moving upwards, this vector right here, I'm thinking about the vector here, it's getting smaller and smaller and smaller, right? In fact, as it's traveling up, its velocity vectors in the y direction are getting smaller and smaller and smaller. Okay? And you'll notice in the x direction, the ball is right here so this is 0 seconds, this is 1 second, this is 1 second, this is 1 second there. So from 0 seconds to 1 second, it's the initial velocity vector in the y direction, and then it gets smaller and smaller. So at the 3-second mark, it's traveled at a constant velocity in the x direction, and now it's at the peak height. Okay? And now, as it starts after the peak height, now it has no velocity in the y direction, and it's now turning around, and now it's going to be falling down. So it's come to a stop here at this point. It's midway from moving up to then moving down. So now it's going to be falling from rest, as if it was just falling from, you just dropped the ball you were holding a ball in your hand and you let it fall out of your hands. Well, now it's going to be speeding up as it's moving down, as it continues to move at a constant velocity in the x direction. Okay? So there's some deductions that we can make about this. So the acceleration vector is always going to be pointed down, right? If you're slowing down as you're moving upwards, that means gravity is going to be acting on you at each point in time. And that again is 9.8 meters per second downwards. Okay. I'm going to make this a little bit bigger. Okay, so gravity is going to be always pointed downwards, okay? All right, well, in the x direction, it has a constant velocity the whole time. Okay, that's one other conclusion that we can make, which is right here. All right? And notice also that it's being caught and thrown from the same height. So that means delta y is going to be 0. Since it's being caught from it's being launched at the same height that it's being caught at, well, delta y is going to be 0. So that's kind of cool. And then at the halftime of flight, so in this case, it takes 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, right? So at this point in time, at the halftime of flight, which is if delta t is 6 seconds, this is the halftime of flight. And that is delta t divided by 2, right? 3 seconds mark. So where it reaches its maximum height is also at the halftime of flight, as long as it's being launched and caught at the same angle, right? So this is 3 seconds, right? Notice also at that 3 second mark, all of its velocity is just in the x direction. It has stopped moving in the y direction altogether. And then now, from the 3 to 4 second mark, it's going to be falling, it's then going to be speeding up from rest and falling to the ground. Okay, so all the velocity in the y direction at that halftime of flight, in the velocity in the y direction is 0. So it's only got a velocity in the x direction at that point, which is just the constant velocity the whole time. So this speed right here is this speed at that point right there. Okay, and so also notice that the length of this, its launching speed, its initial launching speed, is going to actually be the final overall velocity coming in. Those will be the same thing. It's just going to be directed downwards. Okay, so the speed that it is launched at is going to be the speed that it's coming in at. Well, that's pretty cool. That's going to help shape our equations, right? So if we know what to expect, we kind of know how to handle these problems. Okay. There's some other assumptions that you can make, and these are drawn through equations, but I prefer to do the math that shows this, that how far it goes is equal to its initial velocity squared over g sine of 2 theta, and this is theta that is being launched at. But just as a rule of thumb, it actually does work out to that, as long as there's no air friction, okay? And the total change in the y velocity, the total change in the y direction is equal to this too, okay? But again, I prefer to work that out, but if you needed to, you could do that too, all right? But here's some other characteristics that's kind of interesting too about something that is launched at an angle. As long as you don't consider air, it looks like the best launching angle to reach the maximum distance is 45 degrees, right? So as long as you're launching at an angle of 45 degrees, the ball is going to travel the furthest, okay? Notice something really cool. If you launch it at 30 degrees and you also launch it at 60 degrees, it's going to travel the same distance, right? But one cool thing that you could assume, that time of flight, delta t, is proportional to the maximum height, right? What I'm saying is this: the higher something goes, if you throw a ball just 1 meter straight up, it's going to take a half second for it to travel up and then travel back into your hand. But if you throw it 10 meters up, would it take a longer period of time to travel up and then travel back into your hand? Well, yes, it would. So the time of flight, the total time of flight that it takes to move is proportional to how high in the air it got. So this would take most time of flight, right? So this delta t would be greater. So the delta t at 60 degrees is going to be greater than the delta t at 45 degrees. And this time of flight is going to be the shortest time of flight. So I had a friend that was in the Army, and he ran tanks and he ran artillery, and it was kind of cool how they did some things. You know, it was horrendous, but it was kind of, the physics was neat. That they could launch a shell at 60 degrees angle and then launch another shell at a 30-degree angle. And they could make it so as long as they shot this at a 60-degree angle and they waited a certain period of time and then they launched another shell at a 30-degree angle, both of these shells would hit the target at the same time, right? And that's because the time of flight for this 30-degree angle is much shorter because it's not reaching a maximum height as something like this, right? Just incidentally, if you're launching at that angle, you got a delta t is, you get delta y is equal to VIY delta t plus, well, actually minus 1/2 g delta t squared, right? And since these delta t's are on numerators, if delta y goes up, that means delta t's are going to go up as well, right? So that's how I got that analogy. Okay. So again, the higher up an object goes, even though they go the same distance, right here, the same x direction distance, this delta t is going to be a shorter time of flight than this delta t, okay? But as far as and again, we're assuming that we're launching these all with the same initial velocity, right? We're launching all of these with the same initial velocity, and we're launching them all with the same initial velocity, but just at different angles. The one that hits the 45-degree angle is going to travel the furthest. However, the 60-degree angle one is going to take the most time of flight, and then the 45 degrees, and then the 30 degrees, right? So delta t 60 is a greater time of flight than delta t 45, and then finally delta t 30 is going to be the shortest time of flight. Okay, and that's also illustrated here as well. Again, there's a lot of uniformity in motion. So again, I didn't know this. If you launch something at a 15-degree, so all of these are being launched at the same initial velocity. If you launch it at 15 degrees, it'll land at the same distance in the x direction. It'll have the same delta x as something that is being launched at 75 degrees with the same initial velocity. And so that's the 30-degree angle and 60-degree angle here. So on this graph, can you tell me which object is going to take more time in the air? Which one's going to have more hang time? I think time of flight is hang time, by the way. Hang time equals time of flight. Time of flight, that's horrible looking. But anyways, so even though this 75-degree angle one doesn't travel as far in the x direction, that doesn't matter. The fact that delta t is proportional to the maximum height, y max, that means this delta t is going to be greater, it's going to be in the air more than any of these other ones. So this delta t will be greater than this delta t, which will be greater than this one, and then greater than this one, and then greater than this one, right? So even though the 45-degree angle one is traveling the furthest distance, it's actually just, since its maximum height is only here, its time in the air is not going to be as long as the 60-degree angle or 75-degree angle. 75-degree angle is traveling only as far as the 15-degree angle one, okay? But that 75-degree angle one is actually going to be in the air the longest. So it's going to have the most hang time, okay? Now, we talked a lot about free fall, but when you have friction, when you do have to consider air resistance, there is kind of an issue. You don't get this. So with a 45-degree angle, you get this nice parabola, right? But when you launch something with no air resistance, with air resistance, you don't get a nice smooth parabola, right? It gets kind of warped. Right, since it's slowing down in the x direction, if you have friction, your x direction velocity is not constant anymore. It'll have a very long velocity in the beginning, okay? But then that velocity vector will, or that displacement vector will get shorter and shorter and shorter and then shorter over time, right? So it'll be slowing down as it's moving to the right. And so that's kind of warping the shape of this parabola, right? It's not a uniform parabola anymore, right? So it's slowing down the entire time when it goes to hit its angle. And from what I remember is that I think 30 degrees, if you have a perfectly shaped sphere, 30 degrees is the optimum angle to maximize distance with air friction. Without air friction, you hit that ball at a 45-degree angle. Actually, it wouldn't matter what the object is. Just the object, you would just throw it at a 45-degree angle. Okay? So again, here's those assumptions that we make, but we're going to be using the main set of equations that we did at the beginning right here, and we're going to be using this process again. Okay, so we're going to be using that process, and we'll go through it together. Okay, so in a shot put event, you have an athlete that throws a shot with an initial speed of 12 meters per second and an angle of 40 degrees from the horizontal. How far does the shot travel? So let's use whiteboard again. Okay, so again, here's an example of how to work together in groups. Okay, I'm going to snip the problem, use the snipping tool, and we're going to highlight this problem. And now that I have it, I'm going to go to my whiteboard. I'm going to start a new whiteboard session. Okay, and I'm going to paste it in right here. And then I'm going to increase the size of this so I can actually read it. Okay, and again, if I want to invite friends, I could copy the link to bring it in to do that. But right now, I am not working with anyone. It's just me by myself. So here we go. Let's go ahead and try this out. We're going to have a shot putter right here, little person. Okay, and they're going to throw a ball. They're going to throw a ball, and they're going to shoot it at an angle of 40 degrees from the horizontal. So theta is going to be equal to 40 degrees. And this is being launched at 12 meters per second. And that's the initial velocity, okay? And so that means probably somewhere over here, it's probably going to be coming down. When we talked about how things are uniform with a parabola, that it's going to be coming down with a final velocity of negative 12 meters per second. And it's going to be coming down at that same angle of 40 degrees. Okay? Because parabolas are uniform. So it's taking that parabolic path. Okay? Well, before we could list our knowns and unknowns out, okay, we need to find how far it travels. But really, we need to find how the time it takes too. So we need, they're wanting to ask what is delta x, but we need to find what delta t is. Well, before we could do that, we really need to manipulate this right here, because we need to find its velocity in the x direction, its initial velocity in the x direction, which, by the way, is its initial, which will be its final velocity in the y, in the x direction as well. Okay. Because it's going to be a constant velocity, right? Objects move at a constant velocity in the x direction. It's going to be slowing down as it's moving upwards in the y direction, and then speeding up as it's falling down in the y direction over here. Okay. All right. So we're going to need to do a couple things. I'm going to call this initial position 0 in the x direction, and x final is going to be what we're going to be finding, which is actually equal to delta x in our case. All right. So we need to know what its initial velocity in the x direction, and we need to know what its initial velocity in the y direction is. And by the way, that would be its velocity coming down in the y direction as well. The initial velocity in the x direction will be the final velocity in the y direction, but just negative. All right? Okay? Because again, it's part of a parabola. Okay? I'm going to write this a little bit better. V final y is equal to VIX, which is 12 meters per second down and to the right. Okay, so here we go. Let's try finding what the initial velocity in the y direction is in terms of theta and 12 degrees. That is going to be, so this vector is opposite theta, and when I hear opposite, I think sine, so that'll be the initial velocity sine of theta. So that initial velocity in the y direction is going to be up at 12 meters per second sine of 40 degrees. All right. In the y direction, that is going to be 12. It's going to be to the right, 12 meters per second cosine of 40 degrees, because that is adjacent to that angle, right? All right. Here we go. So now let's list out, now that we have the basics and we've analyzed what's going on, I'm going to list out my stuff right here. In the x direction, we need to find delta x. delta x is what we need to find. Now, we know the initial velocity in the x direction, which is equal to the final velocity in the x direction, because it's constant velocity, and that is going to be to the right at 12 meters per second cosine of 40 degrees. We don't know delta t. In order to find delta x, we need to find delta t. In the y direction, well, we know since its initial height is 0 and its final height is 0, we know delta y is going to be 0. Y final minus y initial is 0. 0 minus 0. Okay? We know the initial velocity in the y direction, which is going to be equal to v initial, I'll just put the numbers in, I'm sorry. It'll be launched up at 12 meters per second sine of 40 degrees. We know the final velocity in the y direction is it's going to be coming down at that same speed because this is uniform motion. So it'll be coming down at the sine of 40 degrees. We also know the acceleration, which is gravity, is going to be negative 9.8 meters per second squared. Okay? Again, the only way to link x direction equations to the y direction equations is through time of flight. The time it takes to travel in the x direction at this constant velocity is the same time it takes for it to slow down to a stop and then speed back up and land over here. Okay, and what I'm saying is we need to find delta x. Well, to get that, we need Vix delta t, but we don't know delta t. And so that is going to link our equations. Well, for the y direction, we're going to have delta y is going to equal to, and I'm going to scooch this over a little bit, it's going to be launched up at VIY delta t minus 1/2 g delta t squared. And so again, I'm going to be solving for magnitudes when I do this. But delta y is going to be 0, and what we could say now is that 0 meters, that's 0 meters, and this VIY is going to be 12 meters per second cosine of 40 degrees. So I'm just going to leave this in equation form, and I'm going to solve it. There might be an easier way. You could do this problem two ways, I think. I'm looking at this, and this is delta t squared, and we could use this and use, what is that? Negative b plus or minus b squared minus 4ac over 2a, so the quadratic equation to solve it this way. But I would rather do it the easier way. Actually, let's do it both ways. So this is going to be 0 meters. So I'm going to bring the 0 meters onto the other side. So we're going to have 0 is going to be equal to 0 meters, and this is going to be plus 12 meters per second cosine of 40 degrees. I'm going to center on this now. That should not be cosine, that should be sine of 40 degrees. Delta t minus, so that's 9.8 meters per second squared divided by 2 delta t squared. So I'm going to do some calculator stuff here, and I'm going to find out what these values are. So this is going to just be 0 is equal to 0 meters, and this is going to be plus a number, delta t, and this is going to be minus 4.9 meters per second squared delta t squared. And so let's figure out what this number is right there. So that's going to be 12 meters per second times 40, and we're doing sine. Sine of 40 is 64.27. That's okay. Let's try that again. 12 meters per second times 40 trigonometry sine equals 7.713. So let's call it 7.7. Yeah, let's just call it 7. Let's take it out a little bit. 7.713. So 12 meters per second sine of 40 degrees is 7.713 meters per second. Okay, well, this is a quadratic equation problem, right? This is C, this is B, and negative 4.9 is A. All right? So quadratic equation, there's an easier way to do this I'm about to show you, but quadratic equation again is going to be negative b minus the square root, plus or minus, this is plus or minus, minus the square root of, and I should probably use capital letters for this, that should be b squared. So this is b, negative b, plus or minus b squared, minus 4 capital A, capital C, all over 2a, right? So I'm just going to put those numbers in. So negative b is going to be negative 7.713, plus or minus the square root of 7.713 squared minus 4ac. Okay, so that's 4 times negative 4.9 a times c, which is 0. So that's just going to be 0, all over 2 times a. And this is 2 times a negative 4.9. You have to keep the negative in there. That's a part of that number. All right? So this is going to be 7.713 squared, square root. So this is just going to be negative 7.713 plus or minus 7.713 all over 2 times this. So this is actually negative 9.8. It's kind of funny that we're squaring that. What happened here? This should just be right there. So we took the square root of that, and now we have to, we divided it by 2, and now we have to multiply it by 2. So this is what's going to happen. If you add this to this, right, 7.713 minus 7.713 is going to get, what is that, negative, what is that, 7.713, 7.713 times 2 equals 15.426. So the negative version of this, if this is plus or minus, the negative version of this is, I just forgot that number. What was that, 15.7? 7.713 times 2 equals 15.426. So the negative version of this will be negative 15.426 over negative 9.8, right? If you add this to it, well, this is 0. So basically the solution to this has to be this. It can't, if you add 7.713 to a negative 7.713, that's just 0 over negative 9.8, which is just 0. So this is going to end up being 15.426 divided by 9.8. Which is 1.57. So the time of flight is what we're solving for here. And I just lost that number again. 426 divided by 9.8 equals 1.574. So 1.57. So the time of flight here is going to be 1.57 seconds. All right, there was an easier way to do it, and I thought of it afterwards, and I'll show it to you just to confirm the time of flight, and then we can move on. But there was another way to do this, okay? And it kind of comes from just being intelligent with our solutions, right? So if our initial velocity upwards is positive 12 meters per second sine of 40 degrees, then our final velocity downwards right before it's hitting the ground is just the negative of that initial velocity, correct? Well, we could have done the linear fit of the acceleration of the velocity versus time linear fit, right? Because the v final y is going to be down, right? So that v final y is going to be down, okay? So v final y is equal to v initial y minus gt, right? Well, that v final y is just going to be the negative of the initial velocity, right? Correct? So if you look, oops, I don't know what that is about. So if I look over here, well, the v final y is going to be down and the initial velocity is up. So if it's coming down at that 12 meters per second, that means this final velocity this speed has to be this speed right here. Okay? So essentially it's just the negative of the initial velocity, right? Because this guy, that v final y is just the initial velocity in the y direction, but just downwards, right? So we could bring this onto the other side, and we're going to solve this for delta t, and I should have wrote delta t there. So we need to solve for delta t. Well, we're going to subtract both sides with the initial velocity y, and that's equal to negative g delta t. And then we're going to divide both sides by that negative g. And I'm going to just make that a negative 2. So negative 2 VIY, just add those two together. And then I'm going to divide it by the negative g, which is equal to delta t. This is just equal to 2 VIY over g, which is equal to 2, and that's the initial velocity, which is 12 meters per second sine of 40 degrees all over just the magnitude of the acceleration, right? Hopefully this will work out to be the same number. We know this number right here is 7.713, right? And that's going to be meters per second. Well, this is 2 times that, correct? So this is going to be 2 times 7.713 meters per second over 9.8 meters per second squared. And we know that actually is 15.426 meters per second. So this delta t is the same thing as this one over here. It's 1.57 seconds. Okay? We're not done with the problem, but I just wanted you to find, there's 2 ways to find the velocity as long as you've got this. You could solve it you could solve it a hard way with quadratic equation stuff, or you could solve it an easy way just looking at the linear fit. Okay, well now, since we have delta t, well now we could solve for the delta x. We could solve for how far it goes. Okay, well let's do that. So delta x now is going to be equal to our initial velocity in our x direction times delta t, which is going to be equal to, let me zoom over here, which is going to be equal to 12 meters per second, and it's to the right. And that is going to be cosine of 40 degrees. And we're going to multiply that by our 1.57 seconds. All right, so delta x. Let's do some calculator stuff. So 12 times, and we're going to do 40 degrees, and cosine of that, which is 9.19. 9.193 actually. So this is going to be 9.193 meters per second times 1.57. 9.193 times 1.57. And we get 14.43 meters. And that's how you solve it. I just want to point out, it would have been a much easier problem if I had just done only one of these routes, right? I could have just done this one and just solved it to here, but I wanted you to see how to do it another way, where we kind of do it a more intelligent way in this equation. You know, work smarter, not harder, for example. This is just the bullheaded way. You just do quadratic equation, stick with what you know. But this one you have to think a little bit about, but you find out that the initial velocity, the negative initial velocity is the final velocity. That's a much easier and a much quicker way to solve for the delta t for there. Okay, so that's how to do that problem. So there you go. So next what we're going to do is we're going to combine 1.51 and 1.52, and then so the next section we're going to be solving for problems where it's launched from a height at an angle above a horizontal, and then it's probably going to fall down below. The ball's going to fall down below where it began at. Okay? All right, bye.